Welcome to Esoteric Thoughts. Today I have the great pleasure of welcoming back Dr. Adair. How are you, Aaron?
I'm doing well here. Thank you for inviting me back.
You're welcome. Today we're going to be talking about how we discovered the precession of the equinox. Over to you, Aaron.
All right, thank you. So I try to do some prepping of materials to share because if I talk about equinoxes, vernal points, tropics, things like that, there's just be a whole lot of terminology that's hard to keep track of. So I have some slides that I can use to keep that a little bit more straight away and give some sense of continuity of my thought process rather than just going off the cuff. So the whole idea is that somehow ancient people had developed some knowledge about not just simply the sight of seeing the sun go around the earth, and then a couple people wondering, what if it's actually going around the sun, but other strange motions that really are not detectable except over the course of decades or even centuries. And one of these is known as the precession of the equinoxes. It's this very subtle effect, and some people have claimed that this is extremely ancient, widely known knowledge, while those who study the history of science, history of astronomy, will suggest otherwise. So I'm going to give some of the ways of what some of those other odd claims are, and then what is the more mainstream view on the development of these things. But it ultimately is going to start by looking at this. So whether you're into astrology or not, you have probably heard of someone asking the question, what's your sign? Are you a Pisces? Are you a Gemini? Are you a Libra? I'm a Taurus because I think astrology is bull. Bad joke. But the thing that you will see is these 12 signs that make up the zodiac, of which the sun, moon, and planets move through. The astrologer, of course, has their various ways of interpreting this. But the interesting thing is that the apparent rotation of this entire zodiac over millennia is actually noticeable and detectable with the right tools, and if you take those measurements over a long enough period of time to notice that. So this rotation to the zodiac is obviously something you can't just notice, as you can notice the moon going across the night sky or watch the stars rise and set. This is a much slower and more subtle thing, but it was somehow figured out by people well before the modern era. If you look in some sources, they'll actually suggest it is an extremely ancient piece of knowledge and was well known through myth and folklore for centuries. In particular, if your viewers are familiar with the book Hamlet's Mill, that is probably one of the most well-known sources arguing for this idea that the precession of the equinoxes was just known basically throughout world cultures for millennia, and only in the 1960s did they realize, oh, the ancients knew this the whole time. And really, a lot of it boils down to just like this statement in a 11th or 12th century source, person by the name of Saxo Grammaticus, and basically his stories of the deeds or the doings of the Danes. And this statement here about this mill is allegedly the actual rotation of the sky, and that this rotation is actually representing not simply just the rotation of the apparent stars going from east to west from night to night, but the actual rotation of the cosmos itself as described by the precession of the equinoxes. If you look at the text itself, there isn't like too much there in any sort of details. So the biggest issue that one will say is a lot of what the authors of Hamlet's Mill have done have read into the text. In fact, on a more straightforward reading, it talks about this mill and these things happening not up in the sky, but actually out in the oceans, in the seas. So to say, that when they say seas, they actually mean sky. And when they're talking about the sky, they're talking about the cosmos. And when they're talking about the cosmos, they're talking about this very particular kind of rotation. It's a lot of steps that isn't in evidence. And if you need metaphors to interpret metaphors to then actually get to something extremely precise, this isn't a very great way of making that argument. And the converse is, what did it actually take to actually discover this effect? Because one thing I'm going to try to note here is that this is something you cannot just do with simple naked eye observations over a couple of nights or even over just one simple lifetime, that this required a lot of technology to have been developed over centuries to actually notice this effect. And the first thing we're going to have to do is actually also realize something a little bit strange about that zodiac I showed here before, where you have these nice 12 equal signs. Well, this is actually a bit of extra imagination. So, I mean, not only do you have to look at a constellation and say, oh, that looks like a scorpion, but also some other strange things that are very artificial, but make it much easier to do your measurements. And in particular, it becomes a little bit easier to see what will be the case if we look at the entire night sky. So this is a map of all the constellations up in the sky, both the northern and southern hemisphere stars. So quite a few of these stars might be unfamiliar to northerners. Those living in Australia may not see some of these other stars, but the set of constellations that everyone should be familiar with are right across this wavy line in the middle called the ecliptic. The ecliptic is the path that the sun takes throughout the year. And also along the ecliptic, you will find the moon going along as well as the planets. And that's where you'll find your zodiac constellations. If you look through, you could probably see a couple of noticeable ones. Off on the right side, you can see Taurus, perhaps with its horns. To the left of Taurus, you have Gemini. More towards the middle here, you have Virgo, and so on. You have lots of these constellations, but I also have to be precise and say that these are the constellations. One of those very awkward things in astrology is that the signs of the zodiac have the names of the constellations, but signs and constellations aren't actually the same thing. And to see why there's a distinction, I'm going to circle a few of these constellations. So in particular, in green, I've circled the constellation of Aries, the ram. In the middle, I've circled Virgo, and also in purple, I've circled Ophiuchus. So, as you know, there are 12 signs of the zodiac, and Ophiuchus isn't one of them, even though the constellation itself is in the ecliptic. It actually intersects with there. So there could be 13 signs if we wanted to. Why did we want to have 12? Already 12 had might have been an established number, and the big reason for that is that there are 12 complete phases of the moon in one calendar year. In fact, that's the reason we have 12 months, 12 moons, 12 complete cycles of the moon. Of course, not perfect. Occasionally, you'll get 2 full moons in 1 month, and that's a blue moon. How often does that happen? You might ask that question, and the answer is, well, once in a blue moon. Now, so already to say that there are 12 signs here rather than 13 or some other number is because of some choices that were made by the ancients. But also notice something else is that Aries and Virgo are vastly different in size. Aries is a relatively small constellation, while Virgo is one of the largest in the entire night sky. And yet, on a horoscope, they are identical in size, that they are both said to have a width of 30 degrees, even though Virgo is literally like 3 times the area that Aries is. Now, why do you do that? It actually makes the coordinate system a whole lot simpler to deal with, rather than say, all right, so this took place in the 8th degree of Aries, which how many degrees total on their Aries? If you have a different size for each sign, it gets really hard and complicated. So one of the innovations that had to take place was not only to notice that the sun goes along this path called the ecliptic and goes through these particular constellations, but also create a coordinate system that actually makes it easier to make those measurements so you can track it more easily. Before that was actually done, we can see in old Babylonian records that they'll say such and such planet or the sun is in front of or behind or in a constellation, but that's not very precise. If you want to say down to the degree, down to a fraction of a degree, you need something better than just say, oh, it's somewhere in front. Oh, wow. And of course, where's the front? How big is the front? All these, things that get lost if you don't have that sort of precision. So the first question is then, if we're going to look at the precession of the equinoxes, which affects the positioning of the sun in the zodiac, when does the zodiac actually come into existence as we know it? And we can actually tell what this is looking at old Babylonian records and looking at their observations and the math that they use to actually predict where the sun will be. There's been about a century of back and forth in a history of science studies to figure out more precisely when that is. And generally, you're going to find 2 camps. Those suggesting that the equal size signs of the zodiac came about in about 450 BC, and those in about 400. So as you can see, the argument is pretty small. It's basically a 50-year window that there's any sort of argument, but also 450 BC, that isn't that ancient. This is, after, so many of the ancient stories of Sumer and Babylon. This is well after like the writing of the Epic of Gilgamesh. We're getting down to like the time of Plato when this is actually being developed. And I'll show you a little bit of the evidence of what indicates to most archaeoastronomers or astronomy people that 400 is about the time we think the zodiac came into place. So this is taken from a paper from just about 12 years ago, and it is looking at a series of Babylonian tablets written in cuneiform and their model for trying to predict the location of various astronomical bodies. They had already developed their own, what they call theory of the moon, basically what equation to use to predict where the moon will be on a given date. For the most part, if you're an astrologer, there's two ways you could go about it. You could actually look what was up in the sky, or you can actually predict ahead where it's going to be. And the better you can do a job of that, the better you can inform the king of what's going to happen. If you're going to say, oh, a solar eclipse is coming, well, you'd like to say how far away it is, how plausible that is, things like that. If you just have to say every 6 months, hey, there might be an eclipse, you're going to probably not be a very good secretary if you're not being that informative. So in this model here that these astronomers had worked out, they took the equation that the Babylonians had used to figure out where the sun was going to be and compare that to reality. So we can look at how much error is there between the predictions and what we can actually tell is really the case with modern astronomy. And we can basically figure, 1 or 2 degrees, maybe that's not too big of an error. But once you get to 3, 4, 5 degrees of error, that's a very big noticeable difference. Just to give a sense of size, the moon itself in the sky, a full moon, has a width of about half a degree. So if you're off by, say, 3 degrees, that's 6 moon widths. That's a very noticeable miss if you're wrong about the location of things. So the bigger that error is going to be, the sooner the Babylonians are going to realize, oh, our system is cruddy. So the particular tablet that they were using here in BM 36822 is the name of this tablet. BM because it's in the British Museum. The long number because numbers are boring and this keeps people away. If you make things boring enough, nobody wants to come in and steal stuff, right? So in this tablet, it has these various statements about where the astronomical bodies are going to be, and we can compare that with the equations that seem to come about from there. And we can see that if the model, that the numbers that go into this equation were based on something from around the year 400 BC, then at that time that the model was created, there would have been extremely little error. So you see right here in the middle of this that there's this blue line that is what's something called system A2. It seems to be the system that's being employed by this particular tablet. And if the model was developed somewhere around the year 400, then the error in that model would have been extremely close to 0. It would have been a really good model. But just a couple years out, by the time that this tablet was created, somewhere around 398 BC, already there's about a degree of error in there. So probably getting close to the edge of what is a noticeable amount of error. So this can't be an extremely ancient model. It can't even be a model that's 50 years old because, as you can see, the error is growing a couple of degrees every year. If this model had been used for 50 years, it'd be off by 25 degrees. It'd be off by an entire zodiac sign. So this suggests that this model was created somewhere around the year 400, and they don't have that ancient of observations, accurate observations, to actually make their model better. This is some of the evidence that suggests somewhere around the year 400 is when they start actually having the more precise observations on which they can start developing their models. The models aren't super precise, but with time they will get better as they can compare observations over longer periods of time and with greater accuracy, with greater precision over those long periods of time. But this is already indicating the zodiac itself, as the astrologers use it, isn't that ancient. And if it's not that ancient, you definitely can't talk about how much it's rotating over the centuries. If it doesn't even exist, you can't really talk about how it changes. So the amazing thing is, while the stars have been in the sky for humans for tens of thousands of years, and many of the constellations probably also have significant antiquity, the system of the signs is not nearly as ancient as so much else in ancient astronomy, or the most ancient forms of astronomy that we might be able to reconstruct. Still, though, this is not the actual discovery of the precession of the equinoxes. To get there, we're going to also have to do a little bit more forward going in time and some other bits of precision in our descriptions here. And to see where this goes through, we have to actually distinguish between two different kinds of years. So there's obviously, the calendar that you have on the wall that tells you like what day of the month it is. It tells us that, it's almost Christmas time, etc. But the question of how many days are there in a year, and if we want to be really precise, how many seconds are in a year, we actually have to distinguish between two different kinds of years, one that's called the tropical and the sidereal. Sidereal, it has the old Latin word sidus in there for stars, and tropical for the tropics, like tropics of Cancer, Capricorn. The tropical year is basically the time it takes for the sun to be at a solstice point, go through and return to that same solstice, or if you want to go from equinox to equinox. And also for points of definition, the solstice is the time when the sun seems to have stopped moving up or down up in the sky. It reaches some maximum point, and you either have the longest day of the year or the shortest day of the year, depending on if it's the summer or the winter equinox, and of course if you're in the northern or southern hemisphere. And the equinoxes, as the name suggests, equinox, equal night, when basically day and night are about the same length. And these happen in the spring and the autumn. And the amount of time it takes for that to happen, the simplest form is, or you say there are 365 days in a year. But you also know that we have these leap years every so often. Every 4 years, there's supposed to be a leap year. And that's because it's more precisely 365.25 days for one tropical year, the time it takes for the sun to go from solstice to solstice, or from equinox to the same equinox. However, an even more precise measurement was performed in the 2nd century BCE by a Greek astronomer named Hipparchus. And by using old observations and his own observations of his own time, so by looking at a comparison over a couple centuries, he actually said that the true tropical year is 365.25 days minus 1/300th of a day. So he was able to get down to that sort of level of precision. And if we converted this from days to seconds, this works out to 365 days, 5 hours, 55 minutes, and 12 seconds. Pretty for good precision. This is, a little bit different than the modern value, but it is much more in the neighborhood of that reality. And him having to do these sorts of observations, we'll talk about how he actually does that later. But then we also have this thing called the sidereal year, and that's the time it takes the sun to return to the same position relative to the fixed stars. So if the sun is, say, 5 degrees west of Spica, how long does it take for the sun to get back to that? And the thing is, it's not the same as a tropical year. It works out, according to Hipparchus, when he did his measurements, to 365 days, 6 hours, and 10 minutes. So they differ by about 15 minutes of a year. So that extra 15 minutes, more or less, over 1 year, that is the subtle difference that Hipparchus was able to discover in the 2nd century. And the question is, how do we know that Hipparchus made this discovery? Because if you go to the library and you want to pick up, the written works of Hipparchus, you're going to find out they no longer exist. They are lost works. So the only place that you actually will be able to find Hipparchus's works is where it's quoted in other sources we have. And the main one we have for that is the works of Ptolemy in the book that is usually called the Almagest. I have this copy here, and as you can see, there's a lot of Almagest. This translation is a strong recommendation, so you can actually read this Greek text in English. It's still, of course, very mathematically dense, and it is basically the entirety of all the astronomical achievements that the Greeks and Romans had made up to by about the middle of the 2nd century AD. And Ptolemy quotes Hipparchus a lot. He tries performing some of Hipparchus's experiments on his own to try to improve on Hipparchus, though Ptolemy proved to be nowhere near as good of an observer, so he wasn't actually able to do better than Hipparchus almost 200 years later. So Hipparchus, mad genius in many ways, that how good of a job he did. But how did he actually even figure out the length of these years, and how does that lead to the discovery of precession? So first off, how does one actually go about measuring a tropical year? Well, the easy way you could go and see is, all right, when is the sun at its solstice? And then count how many days is it until the next solstice. Now, if you try just looking at the sun and doing that, well, you'll be blind. You're looking at the sun. That's a terrible idea. You need some sort of better tool to do that. There are ways that you can like figure out when the equinoxes are approximately, but if you really want to be down to the day, then you're going to probably need a more sophisticated tool. And Hipparchus inherited the invention of such a tool, something known as the armillary sphere. This is a drawing of a version of it that existed in the early modern period. The basic things I'll note of this is first that we know who invented the armillary sphere, a guy by the name of Eratosthenes. And if that name sounds a little bit familiar, this is the guy who figured out the size of the Earth based on sticks and shadows in Egypt. And figured out, roughly within 10% the size of the Earth. So Eratosthenes was a pretty smart dude. And he also had developed this tool to basically have like a combination of here's the Earth, here's the celestial sphere around the Earth, and here are some of the major bands that matter to us. And in simplified form, I have here on the right a couple of important circles. One is the ecliptic, that's the path that the sun takes, apparently around the Earth. Again, in the old geocentric model, that's what it would be. And also something known as the celestial equator. So Earth is round, and if you imagine the equator of the Earth projected out into space, that will be the celestial equator. And the other thing to note is the celestial equator is always 90 degrees relative to the North Pole, the North Star, basically. So you can measure where the celestial equator is by measuring from other key stars like that. And you can actually then create a grid to say where the location of all the stars are with effectively a system of latitude and longitude. The other thing to note here is if you look at the ecliptic, it is at an angle to the celestial equator. At the solstices, that's when the sun is at its highest point above the celestial equator or at its lowest point below that. And the equinoxes happen at the intersection point when the sun is right at the vernal equinox, right the vernal equinox. It's a nice intersection between the celestial equator and the ecliptic, and the sun would be directly overhead if you were at the equator. And if you were also at that point, then you would have equal day and equal night at those points. So when Hipparchus tried measuring where the solstices were, he realized that there's actually some trouble. Because the sun barely moves a couple days before and after the solstice, it doesn't really noticeably go up or down that much. It's really hard to be precise when the solstices are. So instead, he chose to actually measure the equinoxes, because then you can more directly measure using something like an armillary sphere and the shadow that the sun casts on the instruments when there is a much more exact alignment between the celestial equator and the ecliptic. So that way you look at the sun shadow where it's being cast, and you can be much more precise to the day on when you actually have an equinox day. Now, if you do that in Hipparchus' time, and if he has a measurement of that from a couple centuries earlier, and according to Ptolemy, he had records of a similar kind of measurement from about a century or so earlier. If you then say, all right, we have an equinox day here, we have an equinox day here, this many solar cycles took place, we can count how many days there are between those two dates, take this number of dates divided by the number of years in there, and then boom, you have your tropical year with great precision. And so the best that Hipparchus could come up with is, he said, all right, it's 365 and a quarter days minus 1/300th of a day. So it was basically really, really close to that, but just ever so slightly off from exactly 365 and a quarter. So that's already pretty darn impressive. Seems like a lot of work, but he decides to keep going because he had read these other records that seemed to suggest that the location of the sun on the equinoxes relative to another bright star, the star Spica in Virgo, had actually moved a couple of degrees over the centuries. So he asked the question, okay, this thing that I just measured, the tropical year, is it the same thing as the sidereal year? Is it the case that the sun not only takes 365 and a quarter minus 1/300th to go from equinox to equinox, is it also the same amount of time it takes the sun to go relative to a star and come back to that same location? And what he discovers is, in fact, it is slightly different by about those 15 minutes that I had mentioned earlier. And this subtle effect suggests a small rotation of either the Earth, and we actually know it's due to the fact that the Earth wobbles like a top. So the axis of the Earth slowly actually goes through this cycle as it wobbles around. There's also an additional effect besides precession called nutation, where the actual angle of the axis changes over the millennia as well. It's an even more subtle effect. So Hipparchus really couldn't detect it, but it seems like he's thought about maybe that's possible as well. And yeah, over the millennia, we can actually measure the effects of precession, nutation. We can also see the effects of the other planets ever so slightly changing the orbit of the Earth on these 100,000 plus year cycles called Milankovitch cycles, which is well beyond what the ancients knew. That's literally a 20th century discovery. But in Hipparchus's view, the Earth isn't necessarily spinning. There were some people who thought the Earth did spin, but most thought the Earth was static. So instead, if the sky seems to be ever so slightly moving relative to the motions of the sun, then it looks like the entire stellar grid is ever so slightly turning, which then is going to change the location of where is the intercept between the ecliptic and the celestial equator. Effectively, it looks like the entire zodiac is rotating around at a very slow rate. When Hipparchus measured that, he said that it looked like a measurement of about 1 degree per century. Now, 1 degree is already a pretty small amount. 1 degree per century, that's a really slow motion. So that's an amazingly subtle effect that he was able to pick up. Now, again, his measurements weren't perfect. He knew that there were imperfections in it itself, and the modern value is closer to 72 years it takes to move 1 degree. So he's off by, 25, 30%, which, when I was teaching physics, if my students in a lab were off by 10%, I would tell them to go and do it again. But all things considered, this is still extremely impressive. And considering he had to use measurements over centuries, I can't tell him to stay in the lab for a couple more centuries to improve on the job. If I told my students to do that, I'm pretty sure I would have been fired, way, way earlier than I probably should have. That's another story. All right. But the question, though, is, I mentioned before Hipparchus using probably an armillary sphere to measure the equinoxes by looking at the shadow of the sun on this device. On the other hand, if you're trying to look at where the sun is relative to the stars, you're not going to be able to use the same tool. And again, you have the problem that you can't just look at the sun relative to the stars, because when the sun is up, how many stars can you see? None. And of course, again, you're looking at the sun, you're just blinding yourself. So you literally can't just go and do those sorts of measurements directly. You need something else that you can actually look at and actually can measure it relative to the background stars. Now, we can't do that with the sun because the sun is just too darn bright. So we need some sort of other object to observe that we can know its position relative to the sun. And the more precisely that we might be able to know that, the better job we can do. You might first think, well, maybe we could use the planets, but the planetary theory is extremely difficult. You notice that the planets not only, of course, move across the stars themselves, but they do these loop-to-loop things. And to actually have a really precise theory that explains that and have it to be as good as you would need to detect precision, you're probably going to have to be in the modern period and have to be a proper geocentrist and using the laws of Kepler or the laws of Kepler to figure out where the planets are. In other words, something Hipparchus could not have done. He did not have that advanced a planetary theory. That was correct. But he did have something else he could look at, and when he looked at it, he would know its exact position relative to the sun. The moon during a lunar eclipse. They knew at that point why lunar eclipses happened. When the Earth and sun are aligned with the moon is behind the Earth in the Earth's shadow, and so it is not reflecting the light of the sun so directly. And they didn't, of course, understand refraction so well, but the light that does get to the moon is heavily refracted, and so it's mostly red light that reaches the moon and turns it to this blood red. But this means during a lunar eclipse, there's an exact alignment between the sun, the Earth, and the moon. So if you observe where the moon is on that night, exactly the sun is 180 degrees in the opposite direction. And because it's an exact 180 degrees, you're like, oh, wow, there's like no experimental error with that. I just have to really precisely measure where the moon is during like the midpoint of that eclipse. And so this is what Hipparchus tried to do. He tried to find eclipses that took place very close to either equinoxes or other important points in the sun's location around the stars. and then measured the location of the moon based on that, and then also found old observations that did the same thing. Now, it's really, really hard to find an observation of a lunar eclipse on the exact same day, like exactly on an eclipse. So he also had to adjust the location of the sun based on his previous work on the tropical year. So if you realize, okay, this observation was like, 3 days before the ecliptic, I need to move the sun 3 days forward based on my previous work. So he had to still, of course, do some adjustments to fix with that, which adds an experimental error. And of course, Hipparchus knew this, so he couldn't be as precise about this measurement as he was with the tropical year. Nonetheless, he could say, hey, there is a subtle difference between a sidereal year and a tropical year. It's subtle, but it looks like it's on the order of 1 degree per century. About 150 or so years later, 200 years later, Ptolemy tries to do the same experiment with observations in his own day. And you would think, oh, if he uses the old observations that would have been like 400 years in his past and his time now, he should have been even doing a better job, because whatever errors he made would have been divided by an even bigger number. But Ptolemy couldn't do that precise of measurements, unfortunately. So he couldn't improve on that. And it took many, many, many more centuries until we got a refined measurement of this precession. Now, as you can see, to be able to measure this effect, you need to have developed a particular model of measuring things in the sky. You have to have that equal size zodiac, so you can actually say the sun is going along the ecliptic, and it's at this degree in the ecliptic based on the constellations is in, but instead of constellations, we have these equal signs. You first have to develop that and start having precise measurements based on that grid system. And we know that grid system only developed around 400 BC. Then you have to develop some of the measurement technology, so that way you can very precisely measure the length of the tropical year. And those precise measurements don't come until basically Hipparchus, and then also his observations of lunar eclipses from over a couple of centuries to very carefully measure this subtle effect. This literally is centuries of observations being written down, having calibrated instruments to do these measurements, and also being aware of any experimental error involved. Which also means that basically, if you're an astrologer, you're not going to go and make your own measurements of the precession of the equinoxes. You're going to probably just, go buy a handbook to tell you the locations of the stars or planets on a given night, or some simple equations to do that, and plug that in. And we can actually see that because we have dozens of old horoscopes from antiquity, and we can actually use that and plot out the location of the sun versus where it really should have been, and we can watch this general trend. So these are mostly from the works of an astrologer by the name of Vettius Valens. He's living in Syria in the 2nd century AD. He has lots of old horoscopes that he used for interpreting. Among the horoscopes he has the horoscope of the Emperor Nero, amongst many other ones, and his own horoscope. And we can actually use his measurements, among others, and see where they're placing things in the sky. And we see this interesting trend about the location of the sun, and compare that to our modern astronomy, and see that there is this difference between the two, but the difference between the two is slowly shifting by about 1 degree per century. It's the effect of precession, which also means that nobody is improving on that 1 degree per century thing. They're basically going in, probably to have some sort of manual with the way of how to do the calculations, so they can grab an abacus, do the calculations for their client, and produce that. And we can follow that general trend. Like, here's a fit line I've done to these measurements. And so you can see it has this nice slope of about 1 degree per 100 years. So if you go from about the year 50 on the left side to the year 150 on the right, it goes from about 5 degrees to 4 degrees. So 1 degree per century is that general trend that you see, just as Hipparchus argued was his best guess at what that rate was. So the astrologers of the time aren't improving on the methods. They're basically, using those and using that to, well, try to have happy clients. How happy they were kind of depends. Some of the things they wrote down were, well, a lot of those recommendations they gave to their clients, they basically say everything, and so they say nothing. They'll say, like, this person will have like lots of different women's in their life, but they're also cold towards women. They won't have any kids, but they'll have all these rascals. It's like they say everything and everything in the middle. So it's very much kind of like a cold reading. If you say enough things and you only remember the hits, it looks like a great psychic prediction, but you go back and record everything and you realize, oh, wow, this person is just flailing. That's what I see in those old records. But nonetheless, this is the general trend we can see. And we can also then figure out, hey, Often people will say something about the precession of the equinoxes will also tell us when the intersection point of the vernal equinox, when that moves from sign to sign, and that's supposed to be astrologically interesting. So already in the 1960s, there's the somewhat famous song, Dawning of the Age of Aquarius, when the vernal equinox is supposed to finally move from Pisces into Aquarius, and then this change of astrological age being super important. Well, now we can actually ask the question, when did the ancients think this would happen? And if we were to go by this, well, if the vernal equinox point was basically off from 5 degrees from where they'd had it, and it takes 1 degree per century, well, in that case, it's going to take 500 years for that movement to happen. So we're looking somewhere in like 500, 550 AD until this is going to happen. So people who are saying that like, oh, this took place at the birth of Jesus, well, they're not doing that based on actual old observations, like in this case here. Very often, like if you look at like where the borders between the various signs are in the zodiac, and they'll tell you, oh, the vernal equinox came into Pisces at the birth of Jesus, or right around the year 1 or 0. They're doing that because they say, well, Jesus was important, so the sky has to say that's important. So the system is fitted to that, rather than let the astronomers of ancient times say what they had. So yeah, if you literally go on Wikipedia, they'll have like 3 different systems on when the astrological age is supposed to begin and end. And it all is dependent on what you're going to actually use as your guide point. The ancients seem to use the location of Spica and measurements based on that. More modern folks are saying, well, Jesus was important, so therefore the beginning of the age of Pisces had to happen right at the birth of Jesus, which is, of course, quite artificial. And as you can also see, here's all the evidence that we needed to figure out how the ancients figured out precession, how they measured it, what technology they needed. So the idea that ancient folks before then, without writing, without these tools, without these measurement methods or systems on the sky, could actually detect and record and incorporate it into their mythology seems like a very stretched argument, or so I and other astronomers would argue.